Hello, everybody, and welcome to our fourth lecture on inverse problems in medical imaging. The outline of today will be the following. We will very shortly recap what we did last lecture, and then we're actually going to perform the singular value decomposition. So we know already what it is, but we didn't talk about how to do it actually. Once we're finished with that, we will start with inverse methods based on length. That's the topic for today and also quite a bit for the next lecture. And then I think in lecture 6 or around that, we will put everything together and you see all the connections between all the different methods we've discussed so far. So we had an arbitrary n by m matrix. So we wanted to solve the inverse problem relating to the non-square matrix. We called the matrix G. We came up with the following. We defined an eigenvector matrix, which we called U, and it contained the eigenvectors of G times G transposed. And if you remember, G times G transposed is a square matrix, and therefore the eigenvalue problem does exist. And then we came up with this arbitrary value P. And if you remember, P was the number of non-zero eigenvalues or singular values. And so when we talk about UP, then we mean all the eigenvectors or that correspond to the eigenvalues or singular values that are non-zero. So please keep that in mind. We will step over it quite often today. Then we defined an eigenvector matrix VP. Again, it consists of eigenvectors corresponding to non-zero eigenvalues. And this time we consider the matrix G transpose times G. And again, G transpose times G is a square matrix, and therefore we can do all the stuff we did. And last, we defined a matrix, lambda. Sorry, there's a mistake. Let's look at it together. The matrix here should be lambda p, not lambda, but lambda p, because we fill the matrix lambda p again with all singular values that are non-zero. So please keep that in mind, lambda p. And if you remember, we said the full matrix lambda will look like lambda p, and then zero blocks everywhere else, where we have here size p, and here size n minus p, and n minus p, where n is the final dimension of the matrix. So we are doing this in 5 steps in total, I think. I guess with all the things we did last week, you will find them rather easy. If anything is unclear, just interrupt me and let me know. Step 1. We start with the problem Gm equals D. And remember, G is non-squared in the general case. And what we do is we build one matrix. We build either G transposed G, which is M by M, or G transposed, which is N by M. And the decision is whichever matrix is smaller. There's a note we can add. So usually N is greater than M because typically we have more observations than unknowns. Step 2. We are going to eigenvalue problems already. So here we just assume that G transpose times G is the smaller matrix. The rest of the derivation is exactly the same if you assume otherwise. We assume G transpose G is smaller. So we have G transpose G times eigenvector Vi equals eta I squared Vi. And there's now two things we're gonna do. First, we would like to find the non-zero eigenvalues. So now we found these non-zero eigenvalues. Step 2. We define the singular values as the positive square root of eta I squared. And number 3, we form the matrix containing the eigenvectors and the eigenvalues, respectively singular values. And remember, once again, we order the eigenvalues so that lambda 1 has the greatest absolute value, followed by lambda 2, and so on, followed by lambda p being the last, and they are all strictly greater than 0. Okay, I keep you a second to look at it before we go to the next page. Let's continue with step 3. We use one part of the shifted eigenvalue problem we had last week. So we use GVI equal to lambda I ui to actually find ui. There's one thing I'd like to note. We basically at the first glance have two possibilities of finding ui. We could also solve the eigenvalue problem for G transposed. So like the other one corresponding to the matrix G. We could do that, and in theory, we would also get the ui's. However, if you remember, we said that the eigenvectors can have arbitrary sign and arbitrary length. And if we use really the eigenvalue problem to find the corresponding eigenvector, then we might not preserve the sign relationship. However, if you're using this equation I've just written down, then we preserve the sign relationship, which keeps us out of trouble. So this is important to remember, please. Okay, let's continue with step 4. This is rather simple. You just form the matrix UP. Finally, we have step 5. you can build T as UP lambda P VP transposed. That's basically everything we need to do. We will leave the singular value decomposition behind us for the moment. We will come back to it next week, where, as I said before, we draw a connection to everything else we did so far. And also during the course of this lecture, you will also from time to time see the importance of the singular value decomposition. What we're going to do next is, when trying to solve inverse problems, is we focus on inverse methods that are based on length. So we still stick to our model problem, that is defined as Gm equal to D, but we do not try to solve this via matrix calculation or everything related to that at the moment, but by using length. What we do is we define two vectors. We define the data error vector. It is D observed minus D predicted. So in here, this observed, means observed. And this pre means predicted. So we have observed data on the one hand, and we have predicted data on the other hand. So for example, predicted by a model or whatever. And the thing is, in here, once we had singular value decomposition and the eigenvectors, we assumed really true data without noise and nice problems and so on. And we know already that the world is not well posed and we have noise every time. So here it is all about noisy data, and you still can solve inverse problem, although you have noise inside. There's another vector we'd like to define, and it's called the model parameter vector M. So it is really nothing else than we had before, but we will use it a bit differently, as you will see in a second. I said this section here is called inverse methods based on length. So we should discuss shortly what length actually is. And therefore, I'd like to recap shortly with you the topic of norms. So what you all, I'm pretty sure, know is that the norm of a vector is nothing else than a measure of its size or length. So this is how we usually use it. There's a few different norms, or actually there's like infinitely many norms existing in the world, but there's a few different we would like to look at. And therefore, we first define a vector E consisting of n data points, so it has length n. And we would like to define three different norms here. First of all, we have the L1 norm. I'm pretty sure you know it already. It is just the sum of the absolute values of all the entries you have. Then we have the LP norm for P being greater than 1 but less than infinity, and 1 and infinity not included here. And it is the sum of all the entries to the P and then everything to the 1 by P. And last missing in this chain here is L infinity, and L infinity is just the maximum entry you have, and from that the absolute value. So you build the absolute value of all the entries and then the maximum. So correspondingly to what I just said, we call the first thing here L1 norm, the second LP norm, and the last L infinity norm. So here written down once again, L1, LP, and infinity. And in practice, we would also write E with, so the original vector, within those norm symbols, and then with 1P or infinity, depending on the norm we actually have chosen. So if you see E and then, for example, in the norm with 2, you know, you have to plug in the 2 norm. There's one important thing. We discuss different norms, and therefore mathematical methods that are based on different norms can correspondingly give different answers. So it really depends on the norm you have chosen. For For example, if you look at the figure top right, you see what different norms do to vectors in the R2. So we have to decide on the norm we choose before we actually go to solve the inverse problem. One last and final note, the L2 norm squared is nothing else than E transpose times E. And if you would like to write it down, this would be E1, En times E1, En, and therefore the sum of the EI squared. I've written it down here because we're gonna use the 2 norm a lot of times, and it might be easier for us if we have this notation here handy. So now that we know about norms, we will start with the first inverse method based on norms. And what we do next is we minimize the misfit using least squares. And we focus for this derivation here on fitting straight lines first. But as you will see here in the lecture and also in the exercise classes that will follow, you can use this method of the least squares for an arbitrary line shape, an arbitrary polynomial shape, or whatever comes to your mind. So when we talk about fitting data to a line, let us look at the left picture here. Assume you have plenty of data points that are depicted here in red, and that you want to fit a straight line through it that is depicted here in blue. So this is basically our aim. We would like to fit it as good as possible. What we do is for each of the individual data points we have, we define an error. So we have on the one hand the predicted data points. As I mentioned before, those are the data points that will be predicted by a model, and the model in our case is the straight line. But then we have the observed data points, and these observed data points are not necessarily the predicted data points. And therefore, there's a certain misfit between those two. And we call this misfit here EI. And for each of the observations we have, we can define the misfit EI as DI observed minus DI predicted. So this is basically with what we start. Now, let us derive the least square solution for the fitting of a straight line. We need a model first, and the model is a straight line. So therefore, DI predicted will be something like M1 plus M2 times ZI. So we have two model parameters in here. They are M1 and M2. And then we have a data point ZI. So M1, M2 are the unknowns. We would like to find them. And ZI is the value along the z-axis. Where the ith observation is made. So in the figure before, you saw that we have plenty of data points, and we assume that the number of data points is n. N data points will lead us to n equations. And what I mean here with n equations is the thing we have written down here. So we will find n of those equations. And we actually can put them together in a matrix notation. So on the left-hand side, we consider d1 to dn. So n of the predicted data points. And on the right-hand side, we have first in the first column 1, then z1 to zn, multiplied with the unknowns m1 and m2. So basically nothing else than an inverse problem with a non-square matrix unless n equals 2, which we would like to solve. We can write this inverse problem in matrix notation once again. And the dimensions would be here, D would be n by 1. Matrix G is obviously n by 2. And the model parameter vector is 2 by 1. Now, what we are going to define, and this is very important, is the so-called total misfit. We define it as E being equal to E transpose E. So this is why I recapped the L2 norm a few seconds ago. And this is then defined as the sum of I from 1 to n, di observed minus di predicted squared. Now remember, for the di predicted, we already have a formula because we decided on the model. And it is the blue thing I've circled at the top of the slide here. So we can actually plug it in, and we end up in I from 1 to n, di observed. Nothing changed with the observed, but in here we have the model. So before we try to solve this thing, there's just a few things we do for convenience. We don't have any predicted here anymore, so therefore we can drop the observed. And therefore di observed will from now on be called just plain di. So one last thing we do. We can now write down E as the sum. And then there's a lot of fun going on. In here we have di squared minus 2 di m1, 2 di m2 set I. Then we have 2 m1 m2 set I, m1 squared and m2 squared set I squared. If you do not believe me, you can do the calculation on your own, or you should do it. You should not believe me. But now the question is, what do we do with this misfit here? I mean, of course, the obvious thing is to minimize the misfit, because then each data point would be predicted as good as possible. What do we do usually when we would like to minimize a function? I give you a few seconds to answer that. Set partial derivative to 0. Yes, excellent, thank you. Let's do that. So we minimize E with respect to m1 on the one hand and m2 on the other hand. So let us do something fun here. The E derived by dm is 2 times. Then we have n, where n is the number of observations we have. m1 minus 2 times the sum over di plus 2 m2, then the sum here again, set I, and this thing should be 0. Number 2. We have minus 2 and then the sum of the di set I. Then we have 2 times m1 sum of the set I. And finally, we have 2m2. And then the sum of the set I squared. And this thing here should be 0. So we can get rid of everything here. And now I just like to copy this thing here onto the next page so that you can see it. Perfect. So we would like to write this thing here in matrix notation because it's just a bit more convenient. And we end up with n on the top left corner. Then we have the sum of the set I, the sum of the set I, and finally the sum of the set I squared. And please note that I just skipped writing the sum of I from 1 to n. We multiplied by m1 and m2. And on the right-hand side, we have sum over d and the sum over di set I. Let us please define a few things here. We call this thing here I, the 2 by 2 matrix. This thing here is m. Nothing really changed with m. And this thing here should be b. And now there's a thing I'd like you to note. So we started with a problem consisting of n equations. And we reduced this rather big problem, if n is big, to a problem with just 2 equations. So we started with this rather complicated problem and made it already way easier. But there's something else I'd like you to note. We do some rewriting next. So the matrix A, which we defined as this thing here, can be rewritten if you look closely into ones, then set I, set n, and the same thing transposed. And this is nothing else than G transposed times G. We can do the same thing for B. So this is the ones here, and the set I's here. And then we have the right-hand side for the observed data. And this is nothing else than G transposed D. So with that, we can define the so-called normal equations for the least squares problem. So we have G transpose G times M equal to G transpose times D. And finally, kind of obviously, we would like to solve this inverse problem we've just seen here. And we find that the solution is G transpose G inverse, G transpose D, but there's already one restriction. Only if this thing here exists. So to recap shortly what we just did, we started with n data points, and we said that we would like to fit those n data points onto a straight line. And therefore, we defined the missed fit. It is the predicted data minus the observed data squared of all the data points. We summed it up. Then we derived this total misfit with respect to the two model parameters. We set it to 0. We did some funny calculation, and we ended up in this thing here being the least square solution. And the thing is, G transpose G, in the form we have it here, is a 2 by 2 matrix. So on the one hand, it has a very small dimension, which is just convenient for us. And since it's a square matrix, we can try solving it or inverting it using the eigenvalue problem. So we started with a rather complicated problem, and we got it down to a very simple problem that will be most likely, depending on G, solvable. Then let's look at another example. I'd like to fit with you a parabola. So compared to before, we have one additional term, and it is m3 times zi squared. So life got just a bit harder here. We assume once again n data points, and we define a matrix notation for this stuff, and we found out that we have something like vector d. Let's assume this thing here is d. Is matrix G times model vector M, and the matrix G has size n by 3. Depending on the number of n, this might be quite hard. Once again, we can calculate G transpose and times G, and it looks rather similar to the thing we had before. But what we have in addition is this column here, where we just have one further level of complexity. And on the other hand, we have this line here, which is the same. Furthermore, we have this vector G transpose times D. It is once again nearly the same we had before, but we have added this term here, which is again one more level of complexity. And finally, we can find the least squares solution as before using the same formula. The difference is that this matrix here is now 3 by 3 that needs to be inverted. So it is still a square matrix, so we can use eigenvalues and eigenvectors to invert it. However, only if all the eigenvalues are non-zero. So if you try now to fit a polynomial of higher order than 3, like we just did, the points you're going to do are exactly the same, like here. And the difference is that the matrix G transpose G and G transpose D, so the vector, will grow in size. So depending on the order of the polynomial you would like to fit, this gives you the size of the matrix and the vector, and therefore inverting also this square matrix will get harder and harder if you do it by hand, but it's still possible. We will go actually to an example that contains numbers. How fun will that be? We will look at something we call a 4-parameter tomography problem. So let us draw a little picture here. Let us assume that we have this funny shape here given, where we have 4 pixels in total. So here we have the first entry, the second, the third, and the fourth. And then let's assume that we sum up on the one hand from the left to the right, and on the other hand from the top to the bottom. So let us assume that we end here in a variable called t1, here in a variable called t2, and then correspondingly t3 and t4. So therefore, we can say that t1 is some scaling factor h times s1 plus s2. So S1 would be the intensity we have on the first box here, S2 in the second, and so on. You can figure out. T2 would be H times S3 plus S4. T3 would be H plus S3. And then finally, and kind of obviously, T4 would be H times S2 plus S4. So we assume that we have the intensities here, the T is given, or the projections. And we would like to find out the density in here. S is actually the intensity of the pixel you have in here. So in the first value here, you would have intensity 1, here 2, 3, and 4. Let's put the 1, 2, and 3 away because that might be a bit misleading for you. Written here, we have an inverse problem. So we have a left-hand side, and it consists of T1, T2, T3, and T4. We just call this parameter vector D. And on the right-hand side, we have this funny scaling factor H. And then we need to plug in all the values we have where we multiplied the S onto. So for the first line, we have 1 and 1, and then 0, 0, 4, 3, and 4. Then we have 0, 0, 1, 1, 1, 0, 1, 0, and 0, 1, 0, 1, multiplied with all the S. And yes, H is just a weight. So, and just to remind you shortly, I've drawn this S1 onto here. And then I mapped the S1 from here, here. Then from this S2 here corresponds to the one here. And the S2 from here corresponds to the S2 here. And then the same thing with 3 and 4. So this 3 corresponds to the one here. And this here to here, and so on. So we define this thing here, including the weighting factor H as G. and here the model parameter vector m. Let's build, like before, G transpose times G. We have H squared. And I'm not doing the calculation with you. I guess you will believe me, what I did on my own before. So we end up with this matrix here. It is a square matrix, so it looks rather nice and good at the moment. Let's calculate the right-hand side. We will end up in this weighting factor H, and then we have T1 plus T3, T1 plus T4, T2 plus T3, and then T2 plus T4. So we can write down the normal equations. They are given as G transpose Gm equal to G transpose D. So the next logical step would be build the inverse. And here's the thing where we run into trouble. We cannot do this. If we calculate the determinant of G transpose G, we find out that it's 0, and therefore no least square solution does exist. So we found a rather simple looking problem where we do not have a solution for. But you will see in half an hour that we find a way of still solving this inverse problem, although the determinant is 0, and therefore we cannot apply least squares. Let's talk for a few seconds about solvability in general. Let us consider that n is the number of observations and m is the number of unknowns. So for example, in the least square fit of a straight line, we had m equal to 2. In the problem we just had here, we had n, the number of observations, equal to 4, and m, number of unknowns, equal to 4. There's 3 possible cases we have here. And please keep those 3 in mind because you will see them a lot in the next couple of lectures. Number 1, even determined problems where m is equal to n. So the number of unknowns is equal to the number of observations. What we can say is if there exists a solution, then the prediction error is 0 and the solution is unique. So for example, consider this very simple 2x2 problem here. We find an exact solution and it predicts both values, so to say, exactly. So this is actually the case we all want to have. Number 2, overdetermined problems where n is greater than m. So we have more observations than we have unknowns. And typically, we cannot fit the data exactly anymore. And this is also the case where most of the time least squares or some form of that are used. So we have the same problem as before, but we have added an additional equation here. So the last one here is added. We try to solve this problem here using the least squares. We find out that the least square solution is the thing or the vector I've just written down here. But if we compare that to the solution we had before, keep in mind here we have 1 and 3, and here we have 1.3 and 4.8. It is different. So using least squares, we have found a solution. but it does not solve all the single equations exactly anymore. It just approximates them as good as possible. And then there's case number 3, underdetermined problems. Here we have more unknowns than observations, and therefore M does not have a unique solution anymore. So we consider the same problem as before, but only with one equation left and all the others are deleted. And here we basically have infinitely many solutions. So as long as we find a data pair M1 and M2 that fulfills this equation here, it will fulfill, it will be a solution to the problem. So if we go back once again to the even determined problem, if you remember when we started with the eigenvalue problem, this was exactly the case we had. We had a square matrix, and therefore we had in this sort of least square fit of a straight line, the same number of observations than unknowns. So therefore, if not because of some miracle one eigenvalue is 0, it would be solvable exactly. The overdetermined case is exactly the case we have in the least squares. And the underdetermined case is the one left. And we start solving this case here today. Again, using length and norms and the stuff here. And we will use the minimum length solution or derive it respectively. And what we do first here is we add some background information. There's 2 things you should suppose. First of all, we assume that the inverse here does not exist, and therefore we cannot build this least square solution. If the inverse would exist, we could just build the least square solution and probably find out if it's equal to the things we are deriving here or not. And second thing, we assume that the prediction error is 0. And please, once again, keep in mind, we said when we have an underdetermined solution, we have many solutions, and therefore also the prediction error of all the solutions would be 0. What we do here is we need to add some information that is not already contained in the original matrix. And we call this information we add a priori information. A sort of a priori information could be solution simplicity, or what we do here, we seek the smallest solution in terms of the norm. So next, we will use all the information we have from the problem definition. But in addition, we require the smallest solution in terms of the norm. And what we use here is a thing you might already have heard about. It's the so-called Lagrange multipliers. So the aim is solve a problem subject to some constraint, whatever this constraint might be. And in the purely underdetermined case, so the one we just looked at, we assume that the constraint we use is that the data misfit is 0. So we're going to do the following derivation for the simplest possible case that comes to our minds. We assume 2 unknowns and 1 constraint. So the goal is to minimize E depending on the two unknowns x and y, so that some constraint is fulfilled. So we say that phi of x and y should be 0. Step 1. We built the derivative of e. So we have partial derivatives with respect to x and then with respect to y. And this thing here should be obviously 0. Step 2. Let's discuss phi for a few seconds. So phi of x and y should be 0. And therefore also the derivative. Sorry. And what this means is that the phi equal to partial derivative with respect to x plus the one with respect to y needs to be 0. So we have two things here already which we would like to have fulfilled. One equation regarding e and one equation regarding phi. So step 3 would be combining this stuff here. And we build a weighted sum. With some arbitrary lambda. And lambda is arbitrary but constant. So we add this lambda to phi. And this is then nothing else if we do some rearranging here. Then first everything here that contains x. And then everything regarding y. And this needs to be 0 once again. Let's put this thing here on another page so that you can see it and I have enough room. Let's go to step 4. So we assume that lambda is chosen so that the first equation therein is 0. Sorry, I missed what phi is. Phi is an arbitrary constraint we just added to our problem. We do the derivation here with phi arbitrary, and then we will use it as plug-in solution simplicity in terms of the minimal norm. So you're probably in a second see when we're doing in a certain example what phi is. So once again, back to the problem, we choose lambda so that the equation regarding x is 0. And then what follows is that the thing regarding phi, y, sorry, needs to be 0 as well. So we call lambda here Lagrangian multiplier. I'm pretty sure you've heard of it before. But what's a bit more important is that we see now that step 3, which I did, is important to a certain equation. On the one hand, the derivative with respect to x of e plus lambda phi is 0. And on the other hand, the same thing holds for y. And step 5. We still need to fulfill that phi of x and y should be 0. And all the three things we have now in our mind. So the equation regarding phi, and then the thing we've written down here, the equations regarding the derivatives of x and y, are summed up to one problem. So we have the thing regarding the derivatives of x. Same thing with y. And finally, phi of x and y should be 0. So we have three equations here, and we have three unknowns, not two anymore. We have x and y. You already know about that. And in addition, we have lambda. So in a second, we will apply this problem here to the purely underdetermined problem and the minimum length, actually. But before, we should just talk about what we're going to do if we have more unknowns and more constraints and so on. So suppose we have m unknowns. And constraints phi of I with I from 1 to n. So back to the original dimensions. And then we have in total m plus n equations. So we have on the one hand all the derivatives with respect to the mi. And on the other hand, we have all constraints. So before we really discuss the questions you might have on this thing we just did here, I actually like to apply it with you to the problem we had previously, because I guess if you see some data and some example you are already familiar with, so within the least squares, the derivation we did, probably life is way easier for you. So the only goal we have, or the only thing why we actually did this stuff here that looked rather complicated, is because we would like to apply it to a certain example. So the problem we discuss we would like to find a model vector M. so that the norm of M is minimized. So that the model prediction error we had before so zero data misfit. And this thing here I've just written down contains your model. For example, if you have least squares, you can go back to M1 plus M2 times Zi, or whatever you want to have. So the total function we would like to minimize is defined with psi. And is M transpose times M on the one hand. And on the other hand, it's all those data misfits multiplied with Lagrangian multiplier lambda. So this is nothing else than this mk squared. And then we have the sum of lambda I, and then inside we have di minus the model. And once again, I got rid of the the observed we originally had. So the observed here is now thrown away in this equation. Next thing, we built the derivative once again. So we derive phi with respect to the model parameters. And we end up in 2 times mq. All the others will be left out. And then for the sum here, the d's will be thrown away during derivation. And left will be the sum here, whereby we have the derivatives of mj with respect to mq. Now, what we can use is that dmj derived by dmq is nothing else than delta j q, so the Kronecker delta. So we use that because life gets way easier if we do so. So d psi derived by dmq is 2 times mq minus the sum of I from 1 to n. And only left will be lambda I. And then g I q, because everything else will be multiplied with 0. And this thing here should be 0 for q from 1 to n. So this equation here we have is very, very simple. We can write it down in matrix notation. So we have 2m minus g transpose times lambda is 0. And therefore, m is 1/2. Okay, this is written a bit ugly. Sorry about that. Let's do it again. G transposed times lambda. So we have come quite far. Let's copy this to the next page. One thing we didn't use so far, and it's the constraint regarding the exact data fit. And if you remember, it was given as D being equal to G times M. So D should be G times M. We plug in M from the thing I've written on top on this slide. So we have 1/2 G transpose lambda, which would be equal to lambda being 2 times G transpose inverse D. With a certain exclusion you know already, only if the inverse actually exists. But finally, we find the minimum length solution as 1/2 G transposed, again from the thing I've written on top of the slide. And then we plug in for lambda 2 times G transposed inverse times D. So it is G transposed times G transposed inverse times D. And that's it. And we are done. So during the derivation, we wanted a perfect fit in terms of the least squares we had before. But in addition, we wanted that the solution has minimum length. So it should be as small as possible. We are not restricted to minimum length. For example, it might make sense that we use a solution, or that we would like to find a solution that deviates as little as possible from some estimated solution. And we just call the solution M in those funny brackets. And if we're doing that, we don't do the whole derivation again, but we just look at the result. In this case, the minimum length solution would be this M plus G transposed times G transposed inverse, so the operator we had already before, and then not multiplied by D, but by D minus G times M. So we defined this thing here to be GML, sort of like minimum length operator. And in this notation, we then have left M plus this GML inverse of D minus GM, which is the same as GML inverse times D plus I minus this funny operator to the inverse times G times M. Now, this thing here looks actually very similar to least squares. The difference is that here we invert G transposed and not G transposed G. So it might make sense if you just compare those two things. So for the least squares, we had the solution given as G transposed G inverse and then G transposed times D, where this inverse operator was given as G transposed G inverse times G transposed. And for the minimum length, we have this funny looking M plus G transposed, and then just in the reversed order, G minus Gm, with GML inverse being G transposed and then G transposed inverse. So just from the other corner around. So this was probably a lot to process for you already today. I just like to finish with one example you know so already. So what motivated us to do the minimum length solution was actually the 4-parameter tomography problem. We had half an hour ago a very simple problem consisting of 4 unknowns and 4 constraints, and we couldn't solve it using the least squares we had. The question is, can we solve this problem now using minimum length? First of all, what we do is we get rid of the linear independent rows we have here. If you look closely at the matrix G, which is still 4 by 4 in the beginning, you see that you can get rid of the last row. So the last row is nothing else than a linear combinations of rows number 1 to 3. And therefore, we don't have any valuable input from this last row. So we get rid of it, we just delete it. Now we have a 3 by 4 matrix left. And we build G times G transposed, which is now 3 by 3. The good thing in this case is that we can build the inverse. And we can also calculate this block G transposed times G transposed inverse. It is written down here. If you do not believe me, try calculating it on your own. And now we just suppose we have some funny model being 1 in the first entry and then 0 elsewhere. We first calculate the forward data, and then we try to build this minimum length solution, plugging in the forward data, and we find out that we can find the model solution again. So using the minimum length, it is now possible to find a solution. It might not be the correct solution. We cannot build a true unique solution, but at least we have found a solution. So we have found in total 3 possibilities of solving inverse problems where we have a different number of unknowns than constraints. So please remember, last week we started with the eigenvalue problem. We said we have a square matrix, and we just built the inverse using eigenvalues and eigenvectors. Then we assumed that we have a non-square matrix. And in the beginning, we used just the singular value decomposition. So we assumed that we have a system of linear equations, and we used the singular value decomposition to find this fundamental decomposition theorem once again, and to use it to build the inverse. And then we said, okay, we would like to include some length. So today we did minimum length solution, which is the thing here. But before we did least square solution. So in least squares, we said we would like to fit as good as possible to some function, which was in our case just a straight line. And we found out this is something nice and something very easy because it leaves us with a very little system of equations. But soon we found a problem, the problem that is just written down here, where it was not possible to solve the problem using the least squares. And then we said, okay, we need to add some additional information. And we did this during the minimum length. So we still said we would like to solve as good as possible in this least square sense. But we said within the example here, the length should please be 0. So we did the derivation once again. And we found out that it actually looks very similar to the least squares, but just the order was a bit changed. And with this minimum length solution, we were now able to solve this problem. So we had 4 possibilities in total. one for the square, three for the non-square. And you will see in the next lecture that they are actually all connected and basically all the same.